So if you think about it, if a language model knows that John Lennon wrote the song Imagine,
Right.
and it also knows that Yoko Ono was married to John Lennon, you would expect it to just effortlessly answer a query, like, who is the spouse of the performer of Imagine?
You definitely expect that. I mean, the facts are right there in the weights.
Exactly. But if you actually probe a standard vanilla transformer on this kind of implicit multi-hop reasoning within a single forward pass, it frequently just freezes.
Yeah, it totally fails.
It retrieves John Lennon in the early layers,
Yeah.
but then it utterly fails to connect that entity to Yoko Ono in the deeper layers. We are basically looking at architectures capable of memorizing vast swaths of the internet, but they suffer from this severe parametric amnesia the second they had to compose two adjacent facts without explicit chain of thought prompting.
It's fascinating, right? Because it highlights a massive structural flaw in the vanilla transformer. Knowledge is basically stored in these isolated parameter silos.
Silos, yeah.
The weights in layer 4 have absolutely no communication with the weights in, say, layer 20. So if a piece of information is retrieved early in the network, the deeper layers cannot flexibly access or route that fact simply because they don't share the same mapping logic.
I mean, it is like having brilliant departments within a massive corporation that share absolutely no internal communication channels.
Yeah.
Department A finds the crucial data, but Department B has entirely different protocols and just they cannot process Department A's findings to finish the project.
That's a perfect analogy.
And this specific bottleneck is the focus of the deep dive today. We're looking at a really fascinating paper from researchers at The Ohio State University, and it's titled Loop, Think, and Generalize: Implicit Reasoning in Recurrent-Depth Transformers.
It's a great paper.
Yeah, and the authors propose a fundamental architectural shift to break down these exact silos.
Yeah.
They basically suggest replacing sequential layers with a recurrent depth, or looped, architecture to tackle two massive hurdles. First, systematic generalization, which is combining completely unfamiliar knowledge. And second, depth extrapolation, meaning reasoning far beyond the complexity the model actually saw during training.
Right. And to understand how they dismantle those silos, we really have to look at the mechanics of the recurrent depth transformer itself.
Okay, lay it out for us.
So instead of stacking unique layers sequentially like we normally do, the researchers take a single standard GPT-2 style transformer block and they literally just loop it.
They just recycle the same block.
Exactly. If you have a block with L layers and you reuse that exact block for R recurrent iterations, your effective computational depth becomes D, which is equal to L multiplied by R.
Right.
And the key here is that the parameters are shared across every single one of those iterations.
Okay, but hang on. Sharing parameters across an unbounded, unrolled depth,
Yeah.
I mean, mathematically, that invites severe instability.
Oh, absolutely.
Because if you unroll a recurrent network infinitely, the gradients are going to either vanish into nothing or explode to infinity.
Mm-hmm.
The input-output Jacobian matrix would become just violently unstable before the model even has a chance to learn the routing. So, how exactly does this architecture survive the backward pass during training?
That is the big question. And the survival of that mathematical foundation relies entirely on their initialization strategy.
Okay.
The authors specifically implemented a zero initialization for the output projection matrices.
Ah, the C-proj matrices.
Exactly, the C-proj. Within the multi-head attention and the feed-forward blocks of the transformer, there are these matrices dedicated to projecting the computed values back into the residual stream. By initializing these specific projection matrices strictly to zero, the entire recurrent block starts its life as a pure identity function.
Oh, wow. So the residual connection is doing all the heavy lifting at step 0.
Percent.
The input goes into the block, the attention and feed-forward mechanisms do their calculations, but because the final projection is zeroed out, literally nothing is added to the residual stream. So Gauss simply equals yen.
Yes. And that guarantees the input-output Jacobian starts as an exact identity matrix.
That's incredibly elegant.
Right. Whether you unroll the loop 2 times or 200 times at initialization, the signal remains perfectly preserved. Gradients flow backwards without any exponential decay or explosion at all.
Because it's just passing the identity along.
Exactly. And from that stable foundation, the model slowly learns to shift the projection weights away from 0. It carefully introduces the routing logic without shattering the stability of the whole recurrent loop.
Okay, so once that mathematical stability is locked in, the architecture obviously has to prove it can actually solve the silo problem we talked about.
Yeah.
And the first major test the paper throws at it is systematic generalization.
Yeah, which is notoriously difficult.
Extremely. Because this is not just recalling facts, right? It is evaluating the model on two-hop inferred facts composed from out-of-distribution or ODE atomic facts. And for anyone listening who designs these systems, ODE evaluation is the ultimate lie detector.
It really is.
These are facts that model has been trained on individually, but it has never, ever seen them composed together in a multi-hop sequence during training.
And vanilla transformers just flatline on this task.
Utterly.
Because of their lack of weight sharing, they have absolutely no inductive bias to generalize a routing mechanism. But the recurrent depth models, even running with just 2 iterations, they successfully generalize to these unseen compositions.
Right, just 2 iterations.
Yeah, just 2.
Yeah.
And mechanistic analysis of how they achieve this reveals a highly distinct phase transition over the training epochs. The researchers actually documented a rigorous 3-stage Grokking process.
Oh, the Grokking dynamics here are incredible to analyze. So stage 1 is purely rote memorization, right? The model overfits the training set incredibly fast, usually in the order of like 10 to the power of 2 epochs. The training loss plummets, but the out-of-distribution accuracy remains pinned at 0.
Yeah, because the network is simply building a shallow statistical mapping from the training prompts directly to the targets. It's not reasoning at all.
It's just a lookup table at that point.
Exactly. But then, after prolonged training, stage 2 emerges. And this is in-distribution generalization. So the model learns to compose facts that share similar structures to what it has seen.
Go.
But the underlying multi-hop algorithm hasn't actually been internalized yet. The model is still relying heavily on localized patterns.
Which means the real breakthrough requires waiting out this massive plateau. I mean, stage 3, systematic generalization, doesn't arise until much, much later. We're talking around 10 to the power of 4 epochs.
It's a huge gap.
It takes an immense amount of prolonged training pressure for the underlying circuitry to fundamentally rewire and unlock the ability to actually compose those ODE facts. I mean, this Grokking dynamic is essentially the difference between a student memorizing a specific math proof by rote for an exam versus finally internalizing the underlying theorem so they can apply it to a completely novel set of variables.
That's exactly what's happening. And to prove that this rewiring genuinely occurred, the authors deployed the logit lens technique.
I love logit lens analysis.
It's so revealing. By projecting the intermediate hidden states of the residual stream back to the vocabulary space at each layer and each iteration, you can essentially read the model's mind as it processes the hops.
Yeah.
You can track the exact moment the intermediate entity, the bridge connecting the 2 facts, becomes mathematically decodable.
Right. So if we look back at the query, the spouse of the performer of Imagine, the bridge entity there is John Lennon. The logit lens shows that during stage 1 memorization, the model just spits out Yoko Ono at the end without ever internally decoding John Lennon.
Yeah, it completely bypasses the intermediate logic.
But then by stage 3, the logit lens reveals a completely different internal state.
Exactly. The model actively decodes the bridge entity in the intermediate layers of the loop. It holds that representation in the residual stream, and then uses the shared weights of the next iteration to map that bridge to the final target.
Because the parameter sharing forces the network to learn a universal routing protocol.
Yes, that's the key. Because the weights are exactly the same in loop 1 and loop 2, the model has to develop a generalized algorithm for retrieving a fact based on an entity embedding, regardless of whether that entity was seen during training or is completely out of distribution.
Okay, so solving the 2-hop problem with shared weights is obviously a massive structural win. But it immediately introduces the question of scaling limits. Like, if the model has internalized the algorithmic rule for 2 hops, can we push it to 10 hops or 20?
Which is exactly what they tested next.
Right, this leads into the paper's second major focus, which is depth extrapolation and inference-time scaling. The researchers basically set up a forced mastery curriculum, progressively training the models on k-hop facts, and only advancing to k+1 hops when the model hit a 95% accuracy threshold on a held-out test split.
And the training efficiency graph under this curriculum reveals another staggering phase transition.
Let's talk about the math there.
For the dynamic recurrence model, learning the baseline multi-hop logic was computationally grueling. I mean, it took over 1.3 million gradient steps just to grok the underlying rules up to 4-hop samples. The model was fighting tooth and nail to build that universal routing protocol.
But once that protocol is locked into the weights, the computational cost to extend it just completely
And
plummets.
falls off a cliff.
The network generalized all the way up to 19 hop sequences, requiring fewer than 8,000 additional gradient steps per hop.
It's wild.
It's like the network stopped learning new facts and simply started applying its internalized algorithm to longer and longer chains.
And this is where we really see the power of separating the training compute from the inference compute.
Right.
To achieve that 19-hop depth extrapolation, you have to increase the inference time iterations way beyond what the model saw during training. So if you trained it on 5 loops, you let it run for 15 loops during inference.
Okay, but the authors discovered that how you train the loops dictates whether this extrapolation is even mathematically possible.
Yes, they compared a fixed iteration model, where the loop count R is kept constant during training, against a dynamic iteration model.
And in the dynamic model, the number of loops isn't static at all. It is sampled per batch from a Poisson distribution. Specifically, it's drawn from a clipped Poisson distribution governed by a parameter lambda, bounded by a minimum and maximum iteration count.
Right, the clipping is important for memory limit.
Exactly.
Oh.
But translating that from the math, it means for any given training batch, the model might get 3 loops or it might get 8 loops. It forces the architecture to be incredibly robust. It literally cannot rely on a specific layer index to execute a specific part of the logic.
That dynamic sampling decouples the reasoning algorithm from the iteration count.
Because it never knows when it's going to stop.
Exactly. A fixed model learns to hard-code its logic to the exact number of loops it was given. If you train it on 5 loops and then give it 10 at inference, its internal representations just collapse because the sequence length is unfamiliar.
Right.
The dynamic model, however, is forced to maintain iteration invariance. Its hidden states must remain coherent whether it is on loop 2 or loop 12.
But wait, if the dynamic model extrapolates better, a skeptical engineer might wonder if it simply benefited from exposure to higher computational depth by chance.
Oh, for sure.
I mean, since the Poisson distribution occasionally samples higher loop counts, maybe it just learned deeper chains through brute force exposure during those rare, long batches.
The researchers anticipated that exact critique, so they isolated the variable. They constructed a controlled study where both the dynamic and fixed models were trained on the exact same data, strictly up to 12 hop sequences.
So no peaking past 12 hops.
Exactly. And even with the training depth capped equally for both, the dynamic strategy matched or significantly outperformed the fixed models, successfully generalizing to 19 hop chains or more.
Wow.
The Poisson sampling itself, the actual mathematical forcing function of iteration uncertainty, is what unlocks the larger learnable recursion depth.
It essentially forces the model to treat the forward pass as a continuous dynamical system rather than a discrete countdown timer.
That's a great way to put it.
But, scaling up inference compute infinitely is not a free lunch. Mathematically, boundless iteration introduces a severe degradation phenomenon that the authors refer to as latent overthinking.
Yes, overthinking is a huge issue here. If you allow the recurrent loop to run excessively, for instance, pushing past 15 iterations on the dynamic model when it's solving a simpler task, the performance curve actually inverts.
It gets worse.
Yeah, the model effectively starts second-guessing itself, drifting away from the correct prediction and hallucinating completely incorrect entities.
It's remarkably similar to a routing algorithm that recalculates its path so many times that floating point drift accumulates, causing it to miss the optimal exit entirely.
That's exactly the mechanism.
And we can see this degradation clearly in the logit margin analysis. For you listeners, the logit margin is the mathematical difference between the logit value of the correct target entity and the logit of the strongest competing incorrect token.
Right. And when you plot that logit margin across iterations, it forms a distinct parabolic curve.
An arc.
Yeah, the margin climbs as the model computes the hops, it hits a reliable peak, and then it steadily decays as iterations continue. Furthermore, the absolute height of that peak margin inherently decreases as the task complexity, the number of hops, increases.
So harder tasks have a lower ceiling of confidence.
Exactly. The model naturally holds a lower maximum confidence for harder tasks, which really narrows the window of success and makes it highly susceptible to overthinking if the loop doesn't terminate at the exact right moment.
Which necessitates adaptive halting. I mean, the architecture obviously needs an internal stopping mechanism.
It has to know when to quit.
Right. Historically, prior works have relied heavily on tracking the KL divergence of the output distribution. The logic was always that, hey, if the change between the probability distribution at iteration p and iteration t plus 1 is smaller than some epsilon value, the model has converged, so you halt the loop.
But this paper proves that relying solely on KL divergence causes the model to halt prematurely.
Why is tracking KL divergence alone insufficient to measure the model's confidence?
Because KL divergence is fundamentally a measure of relative entropy. It only calculates the delta between two distributions. If the output distribution barely shifts between iterations, the KL divergence approaches zero.
Okay.
But that distribution could still be completely uniform, meaning the model assigns equal probability to thousands of tokens. It is highly uncertain, it just hasn't changed its state of uncertainty.
So it has basically converged on total confusion.
Exactly.
Stopping the loop there guarantees a failed prediction.
Therefore, the authors introduced an absolute entropy threshold to work in tandem with the KL divergence. The new halting mechanism requires two strict conditions to be met simultaneously. First, the KL divergence must be small. They set the epsilon to 0.01, indicating the representations have stabilized.
Right.
Second, the absolute entropy of the output distribution must be strictly less than 3.0.
And in information theoretic terms, an absolute entropy below 3.00 means the probability mass has concentrated sharply on a very small subset of tokens.
Exactly.
The model isn't just stable, it is mathematically confident in its prediction. Requiring both conditions prevents the architecture from halting while it is still internally debating the answer.
It is a mathematically elegant dual constraint. It preserves the inference-time scaling capabilities while shielding the forward pass from the degradation of overthinking.
Now, obviously, whenever we discuss models achieving 19 or 22 hop reasoning, we have to interrogate the evaluation data itself. The history of implicit reasoning benchmarks is littered with models that appear to perform miracles, only for researchers to later discover the dataset was basically leaking the answers.
Oh, dataset leakage is the bane of this field.
Truly, previous architectures were lauded for seemingly generalizing to an astonishing 80 hops, but it turned out to be a complete illusion.
Yeah, the models in those prior studies weren't executing an 80-step logical chain at all. They had discovered a mathematical shortcut.
Which is classic neural network behavior.
It really is. The researchers in this current paper used activation patching to expose the cheat. Mechanistic interpretability techniques like activation patching allow us to surgically intervene in the network's residual stream.
So they go in and mess with the hidden states.
Right. They took a clean 60-hop run, which successfully output the correct answer, and they began overwriting its hidden states at specific hops with the hidden states from a completely random, corrupted 60-hop run.
Right, because if the model is genuinely executing a sequential algorithm, corrupting the hidden states at, say, hop 5 should fundamentally destroy the final output, because you have broken the causal chain of logic before it even really gets going.
Yet, when they disrupted the early layers, the output remained perfectly accurate.
That's suspicious.
Highly. The logic margin didn't collapse at all. The network was completely ignoring the first 50 hops. The only time the prediction failed was when they patched the hidden states of the very final relations, the suffix of the sequence.
So the model had learned a shallow statistical mapping. It basically realized that specific trailing relations highly correlated with specific final answers within that specific dataset, allowing it to bypass the intermediate multi-hop retrieval entirely.
It wasn't reasoning, it was just pattern matching the tail end of the query.
To prevent this recurrent depth architecture from falling into the same trap, the authors fundamentally redesigned the evaluation dataset into a permutation-based knowledge graph.
Which is brilliant. They forced genuine multi-step traversal by structuring the knowledge graph mathematically. Every single relation in the dataset acts as a strict mathematical bijection, essentially a random permutation over the entire entity set.
And they used a closed universe of 200 entities with an out degree of 10 for the relations.
Right.
Because a bijection is a strict one-to-one mapping across the entire set, it is mathematically impossible for any suffix of relations to uniquely identify a target entity without knowing the specific starting head entity.
Exactly.
If you don't know exactly where you started, the permutation graph ensures you cannot guess where you'll end up based on the final few steps.
The network is mathematically forced to traverse the entire chain, from hop 1 to hop 22, maintaining the precise entity representation in its residual stream the entire time.
There are no statistical shortcuts available.
None. So when the recurrent depth models equipped with dynamic iteration successfully extrapolated on this specific permutation graph, it served as undeniable proof of genuine algorithmic reasoning.
Okay, so synthesizing all of this for the engineers and researchers listening today, we are really looking at a profound structural evolution here. Standard transformers suffer from parametric knowledge silos, fundamentally handicapping their ability to perform implicit reasoning.
Right.
Recurrent-depth architectures dismantle these silos by looping layers and sharing weights across the depth of the forward pass, and they utilize that clever zero-initialized output projection to guarantee Jacobian stability and prevent mathematical collapse during enrolling.
It's a huge step forward.
And we've seen that systematic generalization to out-of-distribution compositions is possible, but it requires enduring a rigorous three-stage Grokking process where the latent circuitry eventually rewires to decode those intermediate bridge entities. We explored how scaling inference-time compute unlocks massive depth extrapolation, but only if the model is trained with dynamic Poisson-sampled recurrence to enforce iteration invariant representation.
You have to force the robustness.
Exactly. And finally, we dissected the necessity of an adaptive halting mechanism, gated by both KL divergence and absolute entropy to prevent the mathematical decay of latent overthinking.
It really forces us to reevaluate the entire life cycle of a forward pass. We are moving from a paradigm of static layer traversal to dynamic algorithmic execution within the latent space.
Which introduces a highly compelling implication for the broader trajectory of machine learning. I mean, if recurrent depth models can transition from rote memorization to internalizing universal algorithmic rules of composition and do so with a completely static parameter count, what does this mean for the scaling laws that have dominated foundation models for the last 5 years?
It strongly suggests we might be approaching an inflection point. If immense reasoning capabilities can be unlocked by looping a small set of parameters and scaling up the compute during inference, the field may soon pivot away from the brute force approach of continuously scaling up parameter counts.
Yeah, we might hit a wall on parameter scaling anyway.
Exactly. The new frontier might focus entirely on scaling up inference-time latent reasoning, fundamentally changing how we allocate compute budgets between training and deployment.
Leaving us shifting from building impossibly massive static databases to training highly efficient dynamic reasoning engines.